that, it did not support digital modes until recently. So you had to use digital modem software like Fldigi and connect it through virtual audio cable, which is quite an effort for beginner users. And also OpenWebRX uses lossy audio compression between the server and the client, so it's actually not that good for Fldigi. And to solve that, the demodulator needs to be put at the server side and also has to be integrated in the UI. So that was one motivation. The other motivation was adding digital mode support to CSDR, which is a command line tool behind OpenWebRX that I use for DSP. So it's also developed by me, and it can be used to build simple signal processing data flows from the command line, like this one, which is an FM demodulator. I want to add general purpose algorithms for decoding digital modes into this one. And so what about BPSK31? BPSK31 has been invented by Peter Martinez G3PLX. One interesting thing about it is that it uses differential BPSK, which means that it encodes the bits into phase changes instead of the phase state itself. And other thing is that the characters are encoded in varicode. Varicode is a variable length code that maps those letters that are more common in English to shorter bit sequences. And yeah, you can see BPSK31 waveform at the bottom of the slide. And so how do we start demodulating BPSK31? So if you have an SDR hardware, then that gives you, for example, 2.4 megasamples of baseband IQ data. An RTL SDR does that. And we need to select a single channel that contains only our BPSK31 signal, so that we use a digital down converter that's already implemented in CSDR, so I didn't have to work much on that. And okay, we have that single signal, and the next problem is, yeah, it's still a bit oversampled, and we need to decimate it with the correct phase offset, finding the samples corresponding to the maximum power point of each symbol. So, for example, if we select the samples at the red lines over there and use these to decide if we have a 0 and a 1, then we'll have this bit sequence, and we'll have this other bit sequence if we decimate with an incorrect phase offset. And so if we select the other samples, and so it takes care. How do we do it? And that's why there are symbol timing recovery algorithms to help us out. And there are several algorithms for that in the textbooks. And these are just some examples. There are more advanced ones. From these, I've implemented the Gardner and the early late algorithm. And yeah, how do these work? It will be a very informal introduction. Rather than showing you code, I wanted to visualize how do these things work. So very briefly, this implement control loop that readjusts the phase step, readjusts the step in each iteration. So we start from somewhere on the signal. Let's say that this will be the first sampling point. And then we move to the next bit in each iteration. We know how much samples should be one bit, so we know how much should we move on. And then at each point, we calculate an error. So in each iteration, we calculate an error based on our environment or so. This is the formula for the early late gate timing error detector. as in textbooks, and it looks a bit creepy, so we don't understand what it does from this one. But if we say that these are these points, and this this is a simplified formula I've came up with, which is a bit more understandable on how does this work. So based on the error, we readjust our step, and then we move on to the next symbol, or where we think our next symbol is, and again calculate the error, update the step size again, and again calculate the error, update the step size. We always sample in the middle, so that will be the sample that we use to decide which symbol that we have, 0 or 1. And here are some formulas for these algorithms, or I mean these are timing error detectors. And the last two ones are the decision directed, which means that it also takes the symbol decision into consideration. And this is the syntax of the CSDR implementation. And additionally, this algorithm, or this implementation, can use GNU Octave to visualize the internals of the timing error detector, or the timing recovery algorithms. So, yeah, because, for example, I've been playing around with the Müller and Müller clock recovery block in GNU Radio, and it looked like the black box. So actually, I didn't know what it does. It was just, you could see the output and see the input and tune the parameters. But with, in this implementation, I show you that we see live what it does, or we can see if we want. So the other algorithm is the Gardner that I implemented, and there is the formula for it below the graph, and it tries to move the left and the right dot at the top of the symbols, so at the maximum power point, and this is how it is visualized in with CSDR and GNU Octave. So first, yeah, there comes the preamble, and you will see the left dot and the right dot climbing on the top of the symbols. Yeah, it has already done. And if we move past the preamble, it will still stay locked. Just a moment. It's still 101010, and should be coming the data. It's quite a long preamble. Ah, that's it. And still stays locked. Okay, so what other problem can we face while doing this BPSK31 demodulation? The other problem is frequency difference between the transmitter and the receiver LO. So, for example, if we don't tune very precisely with the receiver, then we get something like this at the baseband. So baseband complex signal will look something like this. And this is time domain signal, yeah. This how it looks like if there is some more frequency difference, and it's hard to figure out the bits from there. So we have to do something, and that's what carrier recovery algorithms do to correct for that. And my first try was costless loop on this problem. However, if the user clicked just a few pixels away on BPSK31 signal on the UI, where you can select on a waterfall diagram, it can cause around 40–50% of frequency difference compared to the signal bandwidth. So that's a problem. I had to increase the loop bandwidth much that worsens the tracking variance, and it didn't work like as I expected. But it's in CSDR and it's implemented and can be used for building something else later. But I rather used an algorithm to decode the differential BPSK that's less prone to frequency errors. And I also use the Gardner timing recovery, which is also not much prone to small frequency errors, and these work together really well. And so how does this one work? This takes the last two samples into consideration. So let's say that this is our current sample. And if our last sample was in this range, then actually our demodulator says that if there was no 180 degrees phase change, so it's for example, it's a 0. And if it's in this range, then the demodulator says that it will, there was a 180 degrees phase change, and it's a 1. So that's how it works. And putting this together, we still need a varicode decoder, which is, right now we have the symbols, and we want to get the characters out of that. And we put the bits into FIFO, and if we see that it matches character in the code table, then we output an ASCII byte. So the ASCII character corresponding to the terminal, and that's what this CS0 function does, what's on top of the slide. And it's important to know that there are no varicode codes that contain two zeros next to each other. So the 2 zeros means a separator between characters. And it also helps. And now we can put it together. This is the command. If you enter it into terminal, then it will read from the sound card. And for example, you can try it with Fldigi on a radio signal, and you can then the output is written to the terminal. You can see the first 5 lines or so are the digital down converter. Then comes an AGC, the timing recovery, and the BPSK decoder, and the varicode decoder in the end. And what's interesting about this approach, why I like this, is that by changing a few numbers in this command, you can demodulate BPSK63. And even by changing the numbers, you can set your own speed if you want for BPSK31. So this is it in action. That's the command, and that's the output. And then another thing is that by changing a command a bit, it's also easy to derive new modes that, so for example, here I decided to replace the cosine shape that's used in BPSK31 by default with roost race cosine pulse shape or filters. So I added a root race cosine filter at both the receiver and transmitter, and then the shape of the signal or the output looks like this. It's a bit different from the original BPSK31, but it should have better properties in terms of inter-symbol interference. But although the cosine shape has been chosen, as far as you know, for the low bandwidth, so okay, but it was just an experiment. If I can easily do that, and yeah, as a demo, so how does this look like in OpenWebRX in action? If you can see, yeah, you have to select the BPSK31 mode on the right, then you can select the signal on the left. It has already happened, I think. Okay, so the important part here is what's below the small waterfall diagram. It's decoding one of those signals in the background and writes the output in the browser. So it's OpenWebRX applies the same command in the background that I'll show you a few slides before. And okay. These are the new controls right now in OpenWebRX that were added recently. And I also wanted to show that it's not very advanced to add other modes. These are a few lines that correspond to the BPSK31 demodulator in OpenWebRX, which is written in Python. The CSDR is written in C. Yeah, so this is the same command, or a very similar one to what I've already shown. And this other part in the Python code calculates the parameters for this command. Okay, you also have to make changes to the HTML code a bit to add the new modulation. Okay, so let's talk about Radioteletype. As you can see, it is a plain FSK signal and uses a 5-bit code called baudit code for encoding the characters. And this is one of the demodulator structures I've come up with, or that I tried for demodulating FSK. Of course, I found it in the literature. And this starts with 2 bandpass filters for the mark and the space frequencies, and then follows by calculating the power at the output of these filters, and then subtracts the power, or calculates the difference of the power of the 2 branches, and that's what we get at the output. And then Radioteletype is quite like a serial line, so it's like UART. It's synchronized with the start bit, and then come 5 data bits, and then comes the stop bit. So I decided to write a CSDR function, or add a CSDR function that can decode the data from sample serial line. For example, you could also hook up an ADC on a UART and use the same function to recover data from that. And but here I use it for Radioteletype. And this is the command that decodes Radioteletype from the input is again the audio card, and the output is the terminal. And this is it in action. Yeah, that's the commands, that's the output. Input is generated with Fldigi. Now, I was thinking about verifying that my algorithms are general enough that they work on other signals, not only just amateur digital modes. So I decided that I would demodulate a signal sent by an RF SoC that's used in many products. The Texas Instruments CC1111, which is actually on the yardstick 1 that I've got from Mike. Mike Osman. Thanks, Mike. And so I tried to transmit FSK with this device and receive with RTSDR, then decode with CSDR. And this was the command that worked. So this one, because the packet sent by the yardstick, it reads the input from the RTSDR there and uses the a very similar FSK demodulator that I used for the Radioteletype. but it uses the timing recovery function. I use the BPSK31, the Gardener, and I also use the visualization feature in using CSDR and GNOctave to check that I was actually logged on the, so the algorithm logged and recovers the bits correctly. And then this one is the part that searches for packets in the bit stream. And as a result, so this is it in action, transmitted 100 packets with the RFCAT. So with the RFCAT Python tool that can be used to control the yardstick and decoded them in terminal with CS, or recover the same data with CSDR and output that to terminal. Okay, and few things that are less related but also new in OpenWebRX now is one thing is oh, it doesn't start, it's on the other screen. Okay, so this is a 3D waterfall diagram that I've just added to OpenWebRX. It uses a library called Mapbox to generate a diagram like that in the browser. And the other thing is how the secondary waterfall diagram for the BPSK demodulator can be zoomed by moving the filter shape. In fact, the Radioteletype demodulator will soon be added to the UI as well, because the demodulator itself is ready, but not in, right now only BPSK31 is in OpenWebRX. Okay, and that's all I wanted to show you today, and thank you very much, and I'm now open for questions.